to another session on emerging technologies in the power and renewable space. We have another set of panelists and experts today from various parts of the industry. Um, I think what we'll do is we'll straight away jump to presentations. We'll start with Rimjhim. Rimjhim, if you can, Dr. Rimjhim, if you can just take the podium and take us through your literature.
Hello everyone, a very good afternoon. So today we have the last session I think for the today, and thank you sir for introducing me. I'm Dr. Rimjhim Agrawal and I'm working for Jade Business Services. It's a US based energy tech organization. So we are specialized in data and analytics. We are providing solutions to various industries in different sectors, finance, healthcare, and especially energy. So I take care of all the initiatives which are coming for the energy sector. Now, I'll not take much time in introduction, but yes, so for today, like as we have seen and heard a lot of sessions, right, with India's ambitious renewable energy target as well. Over the past few years, we have seen a lot of enormous progress, right, in the renewable energy deployment. But I would say at the ground, the challenge is no more about the renewable installed capacity. So the challenge is not about the renewable energy installed capacity, but it's more about delivering a power which is predictable and also operationally reliable, right? So to understand these challenges, we should first understand the operating environments where our wind energy or the wind farms or the renewable farms are increasingly operating in. So let me just give a broader context here. As we have already heard from last 3 days, we are understanding and we are aware that India is undergoing a massive renewable energy scale up globally, right? And particularly with wind and solar. So as we move from tens of gigawatts to hundreds of gigawatts, the nature of grid operations fundamentally changes, right? So the forecasting accuracy is no more a nice to have analytics metrics, I can say, but it's actually a grid critical, right? And in the conventional energy power systems, we have seen we did have a control over the predictable output and some sort of control. But wind energy is highly volatile and weather driven. We all understand, right, how wind farm works. Wherever there is a surplus of wind energy, we'll be able to get the wind power. And there might be some seasons, monsoon seasons, where it's a lot of fluctuations happen. So in those scenarios, forecasting becomes very, very challenging. And on top of that, if we have certain sites which have complex terrain and the strong seasonal patterns, it becomes more challenging. The challenges get amplified more. And there may be some orographic influences, coastal factors, and seasonal patterns, which actually create rapid ramps, right? Sudden dips, or the other type of localized variability in the region, which any standard, or I would say a static forecasting methodology, is unable to capture those patterns. And within India, if we talk about the framework, what we are actually aligning with, it's a DSM division settlement mechanism as per the CRC guidelines. So even the small deviation from actual to the predicted or the scheduled generation, it creates a lot of forecasting error, which in turn incurs penalties and huge revenue loss. So then there is a need for an adaptive, modular, region-aware AI forecasting framework, which can actually help in capturing the localized pattern, intraday dynamics, and also the seasonal patterns. So this is what the background is and where I'm coming from, and I would like to highlight that. Now, so to ground this discussion, I'll just highlight one small real-world case study, which is of 50 megawatt utility farm, which is operating in a high variability region. And this site is actually located in the southern part of India, which is a complex terrain, combined with seasonal impacts. A lot of wind monsoons are there, and there is a lot of fluctuations in the wind speed. So those fluctuations are so dynamic and so short duration that it's become, again, it incurs a challenge to the forecasting problem, right? So there we need a strategy so that we can capture those dynamics and produce a forecasting. On top of that, if our operational forecasting horizon, because every forecasting, the first thing which comes to our mind is what is the time horizon or the look ahead period what we are forecasting for. The shorter the time horizon, it becomes more challenging to provide that accuracy because there are a lot of short-term dynamics to capture. Coming to the win, here we are working on intraday, which is 1 to 4 hour ahead. And in Indian context, we are allowed to update several times. Suppose it is 16 times revisions in a day. Then it becomes every 1.5 hours, we are producing a forecast. So that forecast actually, if we are not able to capture any change in wind pattern or just a small delay or the small bias can actually incur a lot of deviation issues, which again results in the penalty, because penalty is a non-linear, so means as the error increases, penalty increases more. That is how the DSM, and as per the DSM framework, it's like a 15 minutes. Our Indian context, it works in a 15 minutes scheduling and settlement happens. That again is a very short span of time. So what I want to highlight here is the short span of time, the time horizon is so less that the dynamics to capture by any model, it's a super crucial and very challenging. Now, before going to the modeling approaches or what we have done to resolve these issues, here I would like to highlight one very important, crucial step which is in data processing about the data quality. We all must have heard in AI/ML, garbage in is equal garbage out. So if for the wind power forecasting, the data, SCADA data if we are giving, if that is not clean, then definitely we will end up paying a huge penalties. So SCADA data, most of us might be, we understand also, it has a lot of noise inherently, and that might be because of sensors, communication issues, or any type of curtailment issues, right? We can see here the blue graph, it's a farm level power curve. And there are a lot of curtailment type of outliers, there are sensor type, communication gaps. The flat horizontal line, if you see, those are because of the curtailment. So those things, if we feed directly into the model or if they're left unaddressed, then definitely these artifacts propagate to the model and they then again reduce the efficiency of the model. So we need to have a robust outlier cleaning approach, and that's what we have done here. We have a 3-stage outlier cleaning process, and you can see here the green color curve, how smooth, stable and meaningful curve it has become. So there is a huge difference between the raw data and the clean data, which directly impacts the modeling approaches, and it becomes the basic foundation. Now coming to the forecasting approaches, we must have heard like a lot of approaches are there, but here what I want to highlight is not about the suite of models. Like every modeling or machine learning models, we tend to have multiple models and we decide among that which one is the best. We do a lot of tuning. But my here idea is to highlight the 2 basic approaches. There's a 2 pipelines here. The first pipeline approach one, basically, so it's an NWP based approach. What does it mean? It's a numerical weather prediction. So this approach is based on the third-party weather forecast, which is actually providing us the weather forecast variables like wind speed, direction, humidity, pressure. So we are depending on an external party to provide us those forecasted variables, and then after doing a rigorous data engineering, like feature engineering, feature selection, they go to the downstream machine learning models or the deep learning models for the wind power predictions, right? So this first pipeline, I would say, is more effective when we have those weather models who are capable of capturing the global geographical variables, right? And the more, if I have to say, there are a lot of things to say due to time constraints. So this NWP, there are global models, there are mesoscale models. So the more resolution models like mesoscale for India, if we have the regional models, NCMRWF is there or IMD is there, rather than depending on the global models, we take the more focused model which can provide the least resolution data, it will be a better for the accuracy. But despite of that, there are certain challenges which we cannot take care just by depending on the weather forecasted variable. So there comes the second approach, which is a pure SCADA driven approach. So in this approach, in contrast to the first approach, we are also predicting the wind speed. Like we are not depending on any third party forecast variable. We are predicting the wind speed based on the historical data using the univariate time series methods. And then the similar approach, what we had in the approach one for the power prediction, we have a suite of ML models, deep learning models, we use it for power prediction. So this particular approach too actually is more responsive when we have short-term dynamics. It is able to capture those very minor things or within a short duration of time that spikes comes, that it is able to capture better than the approach one. And then rather than going or fixing one particular pipeline, what we are doing an adaptive ensemble strategy. In adaptive ensemble strategy, we find the best approach based on the historical performances, like based on the seasons or the month. We can assume like in the monsoon season, certain approach works better, then we decide on that. Or in the non-rainy period, this approach works better, then it is that. So that's here the adaptive ensemble strategy. It becomes a very crucial part and it gives a better forecast. Now coming to the performance, so we did have a lot of performance metrics like MAE is there, MAPE, mean absolute percentage error. But just looking at the lens from the DSM framework as per the Indian context, and this is how the penalties are calculated usually as per CRC regulations. So this is how the results looks, and I would say the adaptive ensemble strategy has really worked well in getting the maximum accuracy. So here how we have defined in the left chart, if you see, there are certain bands, 0 to 15, 15 to 25. So these are the bands which are defined by the policies, governments, Indian Grid Code, and the more number of forecasts we get in the zero penalty band, that is the 0 to 15%, and it is also state-wise. Like in southern state, it is 0 to 15. In the Gujarat, it will be 0 to 10. Just for an illustrative example, here we can see that 90% of the forecasts are in the no penalty zone. So this has come only because we were depending on the adaptive. We are not depending on the one static model or the all fit size sort of approach, but we are tuning it better. And on the right side, you can also see the seasonal variations here. We can clearly see that approach one which I mentioned, it actually gives higher accuracy when you have the stable weather season in the winters or the other non-rainy period. But the approach two, which is on the SCADA driven, as expected, it is much better, or it captures the localized behavior in the monsoon seasons quite better. So there it's a differentiator, and it also explains that why just a single model or approach cannot gives us the DSM compliance, and these are for the annual results, one complete year results are there. Now, so as we have understood, we have demonstrated this case study about the adaptive framework. It definitely helps in getting the net penalties, less penalties, and the more revenue, right? So this is what the agenda was. And but this is not limited only to the wind power forecasting, but it has more meaningful use cases, like in terms of better bidding and dispatch decisions. If we have more accurate wind power or any other power forecasting, then we'll be able to have better dispatch. Now, coming with the hybrid farms, we just saw in the previous sessions also, we have batteries, we have other emerging technologies. So there also forecasting helps a lot in battery, like when to charge, when to discharge. So more accurate we have, it will help in that battery regulations as well. And for the green hydrogen or the data centers, right? So we cannot afford to have an interrupted supply. We should have a continuous one. We should get the more accurate prediction of that. There also wind forecasting, accurate wind forecasting, I would say, helps a lot. So this adaptive framework is not only crucial or critical for the wind power forecasting, but it is actually very important going further for having a more reliable, economical and resilient power system operations.
Thank you.
That's it from my side. Yeah, thank you.
Thank you so much. Please have a seat. We'll invite now Mr. Karunakaran from Tata Power to share his presentation. Mr. Karunakaran.
Good evening to all. I'm Karunakaran on behalf of Tata Power. I am presenting the cases on how to leverage the use of AI/ML for demand flexibility. So everyone will be knowing more about the demand side management. So in this, what's special about this demand side management program is that We call it as a demand flexibility, where we not only reduce the demand, where whenever we have a surplus power, we intend to tell the customer that you increase your load so that we could be able to sell our power, which is mainly a solar power, during the solar hours, so that the distress sale can be avoided. So these are some of the various demand side management programs what we have run through in the organization. Mainly first it starts with the energy efficient appliances program, then we do the power quality and energy audit, then we do the value added services where we use the smart meter data for providing their monitoring their energy consumptions, and we also do some audit for them so that they could be able to reduce their consumptions. And the final one is the demand flexibility programs. We run demand curtailment program, demand increment program, and demand shift program. So what is the peculiar or the new thing in our innovation is that mainly in demand curtailment program we reduces the load, that is the voluntary reduction of load from the customers, and in demand increment there will be the consumer will be suppressing the gas generation and rather they will be using our green power which is cheaply available, and the demand shifting is that shifting of the load to the solar hours. So this is the program flow. What is mainly our AML model says about this. The model will predict that whether to go for a demand curtailment or demand increment. So when we put the load details from the power manager softwares, we get the details whether now we are in a surplus or in a shortage part. So accordingly, our model will predict that, okay, suppose in case we are shortage, so automatically it predicts for a demand flexibility event, so that based on the smart meter data, it identifies who are some of the potential customers who could be able to contribute for the load reduction. So there we use the AML technique to predict the customer who will be participating for our program, and we send a message to those customers. And simultaneously we send the messages just 15 minutes before the program also, so that we could be able to ensure there is a continuous participation of the customers. So in this program we can see there is an integration between our power manager software, the customer relation management portal, meter management, and the SAP ERP also. So there is an integration of all the portals so that we could be able to get a derived result from the program. So as I mentioned earlier, this is the model flow where we have the data stream from the consumer data, and then we check various variables which are contributing to the load factors, and then we model it based on the historical data, and we use the 10 by 10 logics for identifying that how much is the load reduction which will be happening from the customers, and we could be able to predict that how much will be the load curtailment during the program also. So if you see the program, so mainly what happens is that we could be able to identify some of the consumer behavior through the smart meter. So that is one of the key benefit what we are obtaining from the demand flexibility programs. And what happens is that based on these programs, we also run the, we can say that we run the consumer disaggregation also. So appliance-based disaggregation to the customer, so they can be able to identify what are the loads which are contributing their energy consumptions, and what are the options available to reduce their consumption. So these kinds of messages we pass on to the customers through the help of smart meter data, so that we could be able to have some tailor-made solution for the demand flexibility. So in this what happens, if we predict for some 10 megawatt load during our program, we could be able to get the 10 megawatt load basis on this model. So that is one of the peculiar thing about this model. So this is acts as a win-win solution for both customer as well as for the utility. This is the process flow where the customers are voluntarily enrolled, because we float a message to the customers and they enroll, and then we trigger the event through SMS, WhatsApp, and so that the consumer get participated, and then based on the 10 by 10 logics we calculate how much is their reduction of the load, and earlier we are passing the incentives through their monthly energy bill. So basis on this program, demand curtail program, we have got around 1.2 lakh smart meter consumers. So normally we do the event for 2 hours duration, and overall we have conducted around 12 events. We are overall with a cumulative load curtailment of around 140 megawatt, and some of the top contributors are Nesco, Bara Diamond, and some refineries also. The main thing is that we are getting more than around 60 to 70,000 residential customers participating in this program. Even there is a, because as far as the load is concerned, the main contribution will be from the C&I customers, but we are seeing the behavior of the customers that they are voluntarily involving, and more than 60,000, even with the 1.2 lakh smart meter consumer enrolled. For every event, we are getting more than 60,000 customers willingly participating for the event. And for the demand increment program, as I mentioned earlier, there was surplus power available with us during the solar hours. So we approached mainly the refinery consumers and the fertilizer consumers to reduce their gas generations, and we give incentives up to 3 to 4 rupees, so that the overall there is a win-win situation between the utility and the customer. So through this we could be able to sell about more than 40 megawatt load to the customers, where we could be able to use the green power instead of using the gas. And for the demand shifting programs, we are tied up with a BMC, where we could be able to shift around 345 kilowatt of pumping load for 3 hours daily, and mainly we have shifted them to the solar hours, where we have the excess power. So it has contributed to reduce our morning peak, mainly which is due to the heating loads, because at that time, the same time, the pump is also running, so we could be able to reduce that load during this demand shifting program. This is the program way forward. If you see that there is a, if you see the regulation from the MERC, there is a demand flexibility purchase obligation which has been placed over the utility, where the 10% of their peak load should be contributed or to be achieved through the demand response program. So we have already achieved this target. We have contributed around 18.15 megawatt for this DF program. So going forward, we are also looking for automatic demand response programs, where we are tying up with some manufacturers for appliance level. So they will be putting a controller over the appliances and to reduce the load. So this is the overall summary of the event. If you see for demand curtailment event, we have got around 140 megawatt load, and each time we could be able to get average around 110 megawatt. And for the contribution from the RESI is more than 19 megawatt, and C&I is 121 megawatt. So the unique thing about this program is that earlier, as I mentioned, that the incentives were passed on to the customers in the next energy bill. So in this, what happens is that the customer don't have a trust whether I am getting the incentive or not. To motivate the customers, what we have done is that when the program is completed within half an hour, we ensure that the reward amount is gone through the UPI. So that is one of the unique things. We are the first utility to do this, and through the help of smart meter data. So these are some of the consumer experiences. We have Mumbai Metro, MMRDA, TCS, or these are some of the major consumers contributing to our demand curtailment program. And for demand increment program, we have got a BPCL, one of our customers, and Rashtriya Chemical Fertilizers. They help to increase our load during the distress sale times. So this is our BMC load, where we could be able to shift that, and we have identified that there are more than 10 megawatt load available for this demand shifting, and we are pursuing with these customers so that we could be able to shift the power to their solar hours. These are the experience from the main consumers. Thank you.
Thank you. Thank you very much. This is not just energy efficient, also time efficient. I'll invite now Sudhanshu. Sudhanshu, just bear with me. Sudhanshu is from Power Grid. And Sudhanshu will talk about digital twins for proactive anomaly detection in T&D. So over to you, Sudhanshu.
I am Sudhanshu Srivastava from Power Grid Corporation of India Limited. Power Grid Corporation is India's largest transmission company. It approximately is about 85% of India's power, and we are doing domestic as well as international businesses in power transmission. We have footprints in 25 countries, and we are counting. So today my presentation is on digital twins for proactive anomaly detection and predictive maintenance in India's EHV transmission network, finding the data to power paradigm. You all know or would be knowing that the grid is the most essential commodity in the power sector, and with the advent of new technology, especially the green energy, the grid stability is not as it should be, and we have to strengthen our grid. We have to strengthen our grid stability. You would have probably heard there is a power outage in Spain in months of April, where the grid failed within 10 seconds, and that was because that we are using more and more renewable energy in power transmission, and this renewable energy is not stabilizing the grids as the traditional energy does. So to mitigate this instability of grid with the renewable energy, we need something which is smart enough, which can stabilize our grid and all. So for this, we have to adopt smart solutions. So there may be many, but there is a digital twin. Digital twin means that's the replica of the real grid system, which beforehand tells us that what's going to happen in the grid and what's the chances of failure of the grid, what are the parameters, so that we can stabilize our grids, because now the grids are not meant to be maintained by the preventive maintenance or time-based maintenance, because the things are changing very rapidly, and with the green energy integration, the grid stability goes down within the seconds. So now, with the world, India is also going towards the renewable energy, and we are aiming to achieve 500 gigawatt of non-fossil fuel capacity by 2030. But this 500 gigawatt non-fossil fuel capacity, that is renewable energy, would also unstabilize our grid, because the traditional grid has its limitation, and we have to now mitigate this challenge with the smart grids. So now the digital solution that comes with the physics informed machine learning, that is, we are embedding physics, we are embedding machine learning, and we are embedding our traditional technology side by side, so that we can mitigate this challenge. Now the data to power story. We know that India's energy sector is in transition, and there is 500 gigawatt non-fuel capacity target by Government of India by 2030. But this cannot be achieved in the current transmission maintenance scenario, because the current transmission maintenance scenario is based on maintenance, time-bound maintenance, that is, and that's not gonna help with this renewable energy. And we are also heading towards the more and more capacity. Now we are shifting to 765 kV and even 1200 kV assets. So we have to have a strong grid resilience, so that we can bear all this load with the renewable energy. So the next solution can be the data to power architecture, so that we take the data from the grid and we layer this data into four cores. So there will be 4 layers in this twin system. That is a sensing layer, that is a data ingestion layer, and hybrid engine layer, and visualization and decision support layer. And this embedding we will accompany with machine learning that will stabilize the grid data. So we, in this approach, will use physics-informed machine learning, that is purely data-driven deep learning models, because physics itself, that's the physics formula itself, cannot do anything without AI, and AI itself cannot do anything for the grid itself, without knowing about the characters of the electrical parameter. So we combine this physics-informed machine learning with the LSTM. LSTM is a long short-term memory, so that technology that remembers the data patterns, so that we have time-based data patterns, so that we can analyze these data and we can probabilize these data with the Bayesian interface for uncertainty quantification. This is called data to power architecture. So when we use this data to power architecture, so there are 4 layers. First is sensing and edge layer. This layer comprises DG analyzers, PMUs, and UHF sensor. This layer gets data from all the physical parameters of the grid system, that is from transformer, from PMUs, from sensor, from dissolved gas analyzers. And the data is thus collected in the time-stamp form, and then after collecting this data, we go to data ingestion layer. Data ingestion layer is the that takes this all data and standardize this data. And that standardization is should be IEC 61850 compliance, because that is the standard which we have to make. Otherwise, it will be again haywire and the data will not be stabilized. Third layer is modeling core. This layer is the most significant layer, because this layer combines thermodynamics equations, LSTM network, and physics law. So all the parameters are combined in this modeling core layer. And the fourth one is visualization layer, that is the graphical user interface. And this layer helps us to take decision and support and simulation. So we have dashboard, we have risk scoring, and we have remaining useful life, all the estimation in this visualization layer, which we get from other three layers. This is a typical architecture of data to power. We see that there is the sensing layer. Sensing layer takes data from the transformer, it takes data from the base, and it ingests all the data. And these are all raw data, and these are time data. So these all data are coming to the sensor layer, and then these data further comes to the second layer, that is data ingestion layer. And in this ingestion layer, the data is synchronized and it is compliant to IEC 61850. So when this data, all data from all the layers has been synchronized, then there is other layer, that is modeling core layer. Modeling core layer is the layer where all the things happen, where we embed physics laws, where we embed AI, and where we embed LSTM. So based on all these things, all these technologies, we combine the data, we analyze the data, and with the help of physics and probability and Bayesian theorem, we predict that what's gonna happen in the grid system, what's gonna happen to our transformer or our assets. So for the modeling purpose, we have LSTM networks for temporal modeling. You know that direct feed networks, those networks are not good enough for grid failure, because grid data is not very much, it is not in abundance, because we don't have very often grid failure. So we need a data which is over the long time period, and there should be a system which can analyze this data. So this LSTM network temporal modeling, this analyze the data, even the data which is 4 weeks or 6 weeks or 8 weeks old, that it takes that data and it matches that data with the current data. And then we have physics informed constraints, like we combine this data with the physics law, thermodynamics law, so that we know that it is forced by the thermodynamics law, only the data doesn't tell everything. When data is combined with the physics, then we have a real picture. But we have to also quantify whatever is gonna happen. Like in the traditional system, there is like we say that this fault gonna occur in 24 hours or 12 hours. But with Bayesian uncertainty quantification, we tell that there is a 95% probability that this fault will occur within 24 hours. So we have to have quantification of this data. And then there is a robust hybrid predictive framework which combines all these approaches, and we have a data optimization and maintenance. So we can compare traditional grid versus this digital twin grid. So we see that prediction accuracy of the traditional grid, those were reaction based, that was reactive approach. But now we have this forecast approach, where we have prediction accuracy is very high. It is 92% of accuracy in digital twin against 60% in the legacy approach. And false positive rate, that is also reduced to 5%, less than even 5%, because this digital twin approach doesn't consider the false alarm. So even if there is false alarm, so with the comparison of the current data and historical trend, it knows that this is false alarm, so it doesn't give a spike in the probability just looking at that alarm. And this also reduces unplanned downtime to 18%, so that we don't have that downtime, and this boosts our availability. And asset life extension also increases, because then we have dynamic line rating and everything. So we have a life asset extension, as well as if someone new has to come, then that can be deferred. So there is capex deferral as well.
Sudhanshu, please wind up now.
Yeah,
Please
thank you.
conclude. Yeah.
So recommendation is that we have to standardize our data with IEC 61850 compliance, so that we can ingest this digital twin framework in our transformer and grid system, which can embed which can embed and which can help our 500 gigawatt milestone of renewable energy. To do first, we have to prioritize some digital twins on the pilot basis, so that we know what are the problems and we can resolve those problems. And cyber security is also very important, because we are using AI and ML based system. So there comes cyber security. So we have to converge our operational technology and IT together, so that they are aligned with all the guidelines, and it is also ensured that our grids cannot be attacked or hacked. So we know that India is marching towards 500 milestone, and the grid can no longer be managed by static rules in this dynamic world. So digital twin will come as a new visualization tools for grid monitoring, especially when we are in abundance of renewable energy integration with the traditional grid. So I think in future this digital twin will be a major asset in our grid system.
Thank you.
Thank you.
Thank you, Sudhanshu. Very nice and
Appreciate you
insightful
all
presentation.
for listening to me. Thank you.
Thank you. Please have a seat, and moving on from transmission, we have Sunil Kumar. Sunil, welcome again. Please take the podium. Sunil will talk about steam turbine efficiency and flexibility using trace heating technology. So Sunil, over to you.
Yeah, good evening everyone. I know this is the last session of the day, but I'll make sure I don't bore you that much.
Sunil,
I'll be talking about
we'll budget you 10 minutes. Just be efficient.
Yeah, perfect. I will try to
Because
make
we
it
are over
as
shooting
interesting as possible.
Yeah.
So I'll talk about this enhancing the steam turbine flexibility using trace heating technology. Now, first of all, the basic question, why the steam turbine flexibility is required. As we have seen our couple of days, everybody is talking about renewable energy integration, a net zero target mission. So steam turbines 20 years or 50 years back, it was meant for only base load operations. But now coming, renewable is quite flexible in nature. So if you see India energy mix, 50% of current power generation is from thermal, and rest 50 is from other sources. And going forward by 2030, it would be 500 gigawatts from the non-fossil. What it means, our thermal has to go down and should be as a residual load supply compensating the RE power. There are challenges lies ahead of us, like these steam turbines should be quick to respond to the load requirement, and they should be quite fast responsive as and when low demand situation arises. So for this, we have a solution called trace heating technology. What it does, it caters some of the attributes of the flexible operations. Like there are three main criteria of flexible operations. Minimum load, a machine can undergo what is the minimum load, what are the ramp rates, how quickly it can come to the dispatch load, and third is the startup time, how quickly the machine can come to the full load. Like this is like interval between shutdown to the load dispatch time. So this solution keeps turbine in warm condition, and thereby eliminating your holding time and soaking time, and thereby reducing the steam turbine's startup time. And because the turbine is in warm condition, it also boosts up the load change requirement compared to the previous situation. What is, let's say for thermal power, if you see the two curves, red and blue. Blue line shows the natural cooling profile of the steam turbine, and once we activate the hot standby mode, So that red line, it follows, like it does not cool down. Instead, it remains stable or elevated at the temperature. And right side, it is like the difference between blue and red line is like gained by this technology. This is theoretical assessment. I'll take you to the practical implementation of this technology we have implemented. So some of the features for this technology is like this is mounted on the outer casing of the turbine. There are multiple zones defined as per the heating requirement, and all the zones are centrally controlled by an individual control panel based on the requirement. And this is quite robust design. We have done overhauling without any issues. But we should be considerate about the design, turbine design features while, let's say, implementing this solution. Basic principle I'll just skip. This is like heat transfer, like from outer casing to inner parts and inner parts to the rotor, and the life consumption remains low. So if you see this curve 1, this shows the steady state profile temperature distribution of our steam turbine major components, like which are outer casing, inner casing, and the rotor. Once we turn on this hot standby system on, the situation 2, it warms the outer casing and transfers the heat radially inwards, and once it achieves the steady state, it is situation 3, point number 3. So this is like our turbine is in this state, point number 3, and once a load requirement or fast startup requirement arises, so our turbine is in ready to go condition type. I'll show you a quick demo of the temperature distribution which we have predicted, and we have done site measurements from various implemented sites across the globe, mostly in Europe. The predicted temperature profile is in very much precisely matching with the theoretical simulated data. So this is like, now this is the temperature distribution. What are the main benefits of this technology? As I already mentioned, we get a reduced startup time saving. So we almost save more than 60% of the startup compared to the, let's say if we start from normal cold start condition, like our machine is cold, we need to warm it up and then we need to roll it. So we eliminate everything, and the startup machine is quick to load dispatch requirement. Now second thing, we are not exposing the components like hot and cold, so there is no thermal gradient as shown on the previous slide. Mostly my major components are in sync. The thermal gradient across the component is minimal. So the life consumption or damage to the components is minimal, or in other way I can say the cold start of the machines are eliminated, and thereby it extends the design life, because cold startup consumes most of the life. Each event consumes more than 75 equivalent operating hours, and thereby like we are reducing fuel because we are eliminating cold start. We need to burn less fuel during startup. And last but not the least, during startup we are not doing any bypassing, because our turbine is already in warm state. We just need to like maybe few rolling, few minutes of rolling, and then directly sync load dispatch. So thereby we are not bypassing any steam to the condenser, and we saved a lot of energy in that also. So these are nutshell some of the major benefits what we have realized from our practical implementations, and all of these benefits will in turn turn into the cost saving. So this is all, and let's say if you have anything, but at the same time I told like these we should be considerate about design features. So like there is no unit, one solution which fits to all. We have to be consider few design aspects, like while designing, what was the design clearance, like the gap between the rotating and stationary parts, so that during operation there should not be any rubbing or any other operational issue should not occur. At the same time, what is the material combination of various inner parts and outer parts? What is the maximum temperature we can go? So these are some of the design considerations which we need to account before, let's say, rolling this solution or implementing this solution. But there are many worldwide applications of this solution, mostly on KN turbine, and we are investigating for our Indian thermal power plant, which is like majorly governed by HMN kind of configurations, and we will have more to see in upcoming times. So thank you very much. Thank you very much.
Thank you to India Energy Week for having all of us on the dais. Thank you so much. Back to the organizers.